An Introduction to Line Frequency X-ray Generators. This tutorial is presented by Arindam Sarkar. The X-ray generator provides the electrical power sources required for the operation of the X-ray tube. It includes high voltage between anode and cathode, filament heating current, voltage required for the stator winding of a rotating anode tube, controls exposure timing by switching the high voltage on for a desired time and then off, controls the operating sequence of exposure during an exam. The operating sequence of exposure during an exam includes different phases like standby phase, preparation phase, the exposure phase itself, and post-exposure phase before the generator goes back to the standby phase. Controls the operational conditions of X-ray production. The operational control is often accomplished by a microprocessor system, but electromechanical devices are still in use. The operational control includes features like restricting exposure factor selection to prevent X-ray tube overload, monitoring of filament current and anode rotation, etc. Modern generators provide control of the anode temperature by monitoring the power applied to the tube and calculating the cooling time required according to the tube rating charts. The essential generator components are control console that contains kVp selection and high voltage primary circuitry, MA selection and filament heating circuitry for the desired tube current, time selection and timer control circuitry to switch on and off the primary voltage supply for high voltage generation, other support circuitry for operational control, high tension transformer tank that contains high voltage or step-up transformer, rectifiers, filament transformer that is a step-down transformer. The X-ray circuit will be discussed next. We will start our discussion on X-ray circuit through a simplified block wiring diagram. Power supply line. An incoming single-phase or three-phase AC voltage supplies the X-ray generator. Autotransformer. The line voltage is fed to an autotransformer of the X-ray generator. This autotransformer provides variable voltage output through a kV selector switch. The output voltage of the autotransformer is called the HT primary voltage. Timer circuit. The timer circuit switches on and off the HT primary voltage as per the set exposure time. High voltage transformer. When the timer circuit switches on the HT primary voltage, the secondary side of the high voltage transformer steps up the primary voltage to kilovolt range. Rectifier circuit. The high voltage AC output from the high voltage transformer is converted to DC voltage by the rectifier circuit. The high voltage DC output of the rectifier is fed to the X-ray tube with positive voltage to the anode and negative voltage to the cathode. The path from autotransformer to the rectifier circuit output forms the main circuit. MA selector. The MA selector is fed with a fixed voltage from the autotransformer. The MA selector allows selection of tube current from available discrete MA stations. Filament transformer. The MA selector applies the required voltage to the primary of the filament transformer. The filament transformer steps down AC voltage from the autotransformer and MA selector to smaller AC voltage. This AC voltage is connected to the X-ray tube filament for heating the filament to produce the required tube current. The path from the autotransformer to the filament transformer output via MA selector forms the filament circuit. For a rotating anode X-ray tube, a rotor control circuit is additionally required for supplying power to the stator windings of the X-ray tube. Having reviewed the block diagram of X-ray circuit, let us discuss its different components. The line voltage from the wall plug-in is supplied to the X-ray machine through an overload protection fuse or circuit breaker and an on-off switch. The voltmeter measures the voltage from the wall plug-in, and accordingly the line compensator tapping of the autotransformer adjusted for stabilized 220 volt output. The autotransformer has a single winding and sends voltage to the filament and high voltage circuit. The autotransformer, also called the variable transformer, works using alternating current, is self-inducting, and has only one winding. The autotransformer is provided with taps to select a HT primary voltage corresponding to the required kVp. The kVp meter, or the pre-reading voltmeter, is calibrated to display the voltage in kilovolt that will be applied across the X-ray tube once the exposure is made. Next is the exposure contactor with a timing circuit, which is used to complete the X-ray exposure. The timing circuit initiates and terminates the exposure, as well as regulates the length of the exposure. Now that we are finished with what's in the control console for the main circuit, let's move on to the high voltage tank. Here we have the step-up transformer, which increases the voltage to kilovoltage for X-ray production and still operates on alternating current like the autotransformer. But here we have two fixed windings, one primary and one secondary, that operates on the principle of mutual induction. The secondary winding typically has 500 to 700 times more turns than the primary winding. The tube voltage is supplied symmetrically to the tube. For instance, a net potential difference of 100 kV is achieved by feeding -50 kV to the cathode and +50 kV to the anode. This is electrically accomplished by grounding the center tap of the secondary coil of the high voltage transformer. An MA measuring circuit and an MA meter is included at this point. The MA measuring circuit includes a bridge rectifier circuit to measure the current in the secondary circuit, that is the tube current. The step-up transformer links to rectifier diodes, which converts the alternating current into direct current for the X-ray tube to use. In this circuit, 4 rectifier diodes are attached in the form of bridge circuit. Mostly these rectifiers are made of silicon just for their compact size, good current ratings, and their durability over time. Now that we have completed our discussion on the main circuit, let's move on to the filament circuit. A fixed voltage tapping provides the power to the filament circuit. Here we have the MA selector, which selects the required tube current. The MA selector is connected to the filament transformer through a resistor bank that controls the current supplied to the filament transformer. Here, instead of a step-up transformer, we have a step-down transformer, also called the filament circuit transformer, which decreases the voltage and in turn increases the amperes going to the filament. Finally, the anode of the X-ray tube is connected to the positive side of the rectifier output. The cathode of the X-ray tube is connected to the negative side of the rectifier output. The applied potential difference in the range of kilovolt causes the thermionic emitted electron cloud from cathode filament to accelerate towards the anode with high kinetic energy. The anode serves as a target surface to impede these accelerated electrons and transform their kinetic energy to X-rays. All of these discussed components make up the X-ray circuit. The X-ray circuit is divided in different ways. While discussing block wiring diagram, we saw that the X-ray circuit can be divided into the main circuit and filament circuit. The main circuit creates the X-rays by modifying the power from the source. The filament circuit, on the other hand, ensures that by using the incoming power the filament produces suitable amount of thermically emitted electron cloud to produce the required tube current during exposure. The main circuit can be further divided into the primary and secondary side of the X-ray circuit. The primary side consists of the autotransformer, kV selector, exposure contactor, and the primary winding of the HT transformer. The secondary side contains the secondary winding of the HT transformer, the rectifier diodes, and the HT cable supplying the high voltage DC to the X-ray tube. The last way the X-ray circuit can be divided is based on the physical location of the components. The three physical locations are the control console, the high-tension transformer tank, and the X-ray tube that forms the parts of the X-ray machine. All the discussed components of the X-ray circuit can be found within these three physical locations. We will now move forward to briefly discuss about few alterations in the X-ray circuit to accommodate additional or enhanced features. Mains matching resistor. The impedance of the mains supply can vary from installation site to site or due to changes in other factors in a particular site. This impedance can affect the output of the high voltage transformer due to drop in the primary voltage during an exposure. To compensate for this, a mains matching resistor is sometimes used in the circuit. This resistor is connected in series with the autotransformer input and can be adjusted so that it matches the impedance of the mains supply considered while designing the X-ray machine. The kV primary voltage selection accounts for the voltage drop during the exposure for different tube current. This helps in achieving the accurate and stable kV output of the high voltage generator. kV selector. Some X-ray machines are designed with two kV selector knobs, kV major and kV minor, that allows for a finer control over the output kV by providing a coarse and fine adjustment. This helps in achieving the desired output kV and also reduces the number of tapping needed in the autotransformer. The kV major selector has a larger number of taps, usually ranging from 40 kV to 125 kV or higher in multiples of 10 and provides a coarse adjustment. While the kV minor selector has a smaller number of turns for each tap, which provides a finer adjustment typically in the range of 0 to 10 kV, and allows for kV adjustments in increments 1 kV or even smaller increments. In some newer X-ray machines, carbon rollers are used instead of the taps on the autotransformer. Carbon roller work by varying its contact area on the autotransformer winding to adjust the output voltage. This method is more precise than autotransformers with taps and is also more efficient. Such machines also use carbon roller for the mains voltage compensation, which can be designed to automatically compensate for any fluctuation in the supply line voltage. Mains on-off. Instead of manual on-off switch, relay contactor with soft touch on-off control can be implemented. The on-off circuitry uses a relay contactor with one or two main contacts and one auxiliary contact. All are normally open or NO contacts. Two push-button switches are provided on the control console. These push buttons are connected in series with the relay call. The off push button is NC and the on push button is NO. When the on push button is pressed, current flows from the live to neutral through the off and on push buttons and the relay coil. This energizes the relay and its main and auxiliary contact closes. The closure of the main contact switches on the X-ray machine. At this moment, if the on push button is released to go back to its NO position, the current through the relay coil keeps flowing through its own auxiliary contact, which is connected in parallel to the on push button. This configuration of the auxiliary contact is also called self-holding contact. The X-ray machine continues to be in this switched on state until and unless the off push button is pressed to break the current flow through the relay coil. So by pressing the off push button, the X-ray machine switches off. In this filament circuit, a filament voltage stabilizer is used to provide an accurate voltage to the filament circuit, irrespective of the fluctuations in the line in from the autotransformer. To minimize the thermal stress while boosting the filament current during exposure preparation and to increase durability of the filament is permanently preheated during the standby condition to a temperature for which thermic emission is negligible. To accomplish this task, during standby condition, a lower power supply voltage is selected through the NC contacts of a filament circuit relay to preheat both foci. Preheating rheostats is provided to adjust the preheating filament current. During the preparation stage of exposure, the filament circuit relay is energized, causing NC contacts to open, thus stopping the preheating current. In this stage, the NO contact closes and higher supply voltage is selected to boost the filament current for sufficient thermic emission to supply the desired tube current. The MA selector is configured in this circuit to supply a dual-focus X-ray tube. The lower MA selections are connected to the small focus and higher MA selections are connected to large focus of the X-ray tube. Space charge compensator. Normally, to increase the tube current, the filament current needs to be increased. However, at lower kV and higher filament current, the tube current is limited by the space charge effect. In this condition, if the applied kV is increased, the tube current will rise without changing the filament current. To compensate for this space charge effect, a space charge compensator is used. The space charge compensator is a device added to the filament circuit that automatically lowers the filament current as the kV is increased. This keeps the tube current constant. In this illustration, a multi-tap resistor is used for space charge compensation. This resistor is connected to a rotary switch that is mechanically coupled with the kV selector switch. When an higher kV is selected, more resistance is added to the filament transformer primary circuit, thus helping to lower the filament current. Finally, the generator is programmed to set the heating current according to the tube characteristics. The heating currents range up to 10 ampere with voltages of less than 15 volt AC. Exposure time control is achieved in different ways. 1. Mechanical. This method is now obsolete. 2. Electronic and measuring. Based on time calculated with quartz crystal or based on measuring the power line pulses. 3. Automatic exposure control. This method is used to terminate the exposure based on the radiation received by receptor, that is, phototiming radiation detector. There are different types of phototiming radiation detectors. 1. Screen and photomultiplier tubes or PM tubes. This type of detector is now obsolete. 2. Ionization chambers and 3. Solid-state detectors. Ionization chambers. This is almost always entrance-type detector, that is, they place before the screen film. The ionization chamber contains electrodes made of thin parallel aluminum plates and the chamber is gas-filled. When voltage is applied between electrode plates, they collect ions produced by radiation in gas between electrodes. This collected ions produce electric current. This electric current is proportional to the X-ray dose received by the ionization chamber. Solid-state detectors. PN semiconductor junction generates current when struck by radiation. This type of detector is small in size, with fast response and negligible beam attenuation. Phototiming fields. 1, 2, or 3 fields may be selected individually or in combination depending on the part to be examined. Here proper patient positioning is critical. Phototiming circuits must be calibrated for particular film screen system. Some generators allow selection from several preset film screen combinations. For safety, if the phototimer does not terminate exposure, the exposure is limited by a backup timer set for maximum MAs. As we are on the discussion on timer circuit, we will briefly discuss on a modification made in the exposure timer circuit for many high MA machines. Here, instead of one exposure contact, 2 contacts are used. The timer circuit actuates the one contact first. This energizes the HT primary through a damping resistor, R. This damping resistor restricts the magnetizing inrush current of the HT transformer. After few milliseconds, the timer actuates the contact E2 that bypasses the damping resistor, allowing the full HT primary voltage. Another method of reducing the magnetizing inrush current is done by the timer circuit is by monitoring the line voltage and switching on the exposure contact at zero crossing point. We will briefly discuss about the rotor circuit next before discussing about rectifiers and ripples. Rotating anode X-ray tube works on the principle of single-phase induction motor. 2 stator windings are provided separately for this purpose. The anode functions as a rotor of this induction motor. A separate circuitry is required for energizing its stator coils during preparation and exposure. A simplified diagram is illustrated here to understand the operating principle of the rotor circuit. During the preparation, contactor S is closed to supply power to the 2 stator windings. The starting winding is connected to the 0V through a capacitor C to provide the necessary phase shift required to create a rotating magnetic field. After a short time delay, allowing for anode acceleration, the contactor S opens and R closes to provide the reduced supply voltage to the stator windings for maintaining the running condition. After the exposure, the contactor B is switched on with a delay to supply DC braking power to the stator winding through a diode. The delay in activation of the braking contact is imposed to keep the anode rotating. Here exposures are initiated at short interval. Else frequent braking may cause overheating the stator winding. Half-wave rectification. Some low-power X-ray units use the X-ray tube as a self-rectifying diode. In this arrangement, the current flows through the X-ray tube when the applied voltage to the anode is positive with respect to the cathode. But in the self-rectifying diode, there are high chances of reverse current flow as a result of a hot anode. This is a limiting factor as this may damage the X-ray tube. This rectification method is rarely used because of this disadvantage. Nowadays, solid-state diodes are used as rectifiers for half-wave rectifier circuit. The X-ray tube is connected to the secondary of high-voltage transformer through the diode rectifiers. Half-wave rectification results in a one-pulse or single-pulse waveform. For a mains frequency of 50 Hz, a pulse duration of 10 milliseconds is produced with 10 millisecond gap between these pulses, producing 50 pulses per second. Since only positive half cycle of high-tension transformer is used and the negative half cycle is wasted, this rectification process is inefficient. This rectification method is used only for very low-power X-ray machines like dental application where the extra cost for rectification have not been accounted. Full-wave rectification. 4-diode in-bridge configuration is connected to the secondary of the single-phase high-voltage transformer. The rectifier reverses the negative half cycle and applies to the X-ray tube. So both the positive and the negative half cycle of the high-tension transformer is used. Full-wave rectification results in a 2-pulse waveform. For mains frequency of 50 Hz, 100 pulses per second are produced. The pulse duration is 10 milliseconds with no interval between the pulses. The output is double that of half-wave rectifier. In single-phase rectification, both half and full-wave rectification produces waveform with 100% ripple. 3-phase rectification with 6-pulse output waveform. In this arrangement of rectification process, 1 delta primary with 3 windings, 2 Y secondaries, total 6 secondary windings, 2 diodes per winding with total 12 rectifier diodes are used. The use of 2 Y connections in the secondary side of the transformer gives 2 secondary voltages with a common ground and symmetrically splits the applied tube voltage to positive and negative with respect to the ground. With a 3-phase mains supply, 3 AC voltages with a phase shift of 120 degrees are available, so that at any given moment, one or more phases have a non-zero voltage. This results in a more continuous and stable output voltage compared to a single-phase power system. Full-wave rectification of this 3-phase AC produces 6 half-waves per period, that is 6-pulse waveform. The nominal ripple of 6-pulse waveform is 13.4%. Due to imbalances in transformer windings and voltages, the ripple might in practice approach 25%. 3-phase rectification with 12-pulse output waveform. In this 3-phase rectification, 12-pulse circuit, 1 delta primary, 1 delta secondary, 1 Y secondary, total 6 secondary windings, 2 diodes per secondary winding, total 12 rectifier diodes are used. As we already saw in 6-pulse rectification process, that each secondary windings produce 6 pulses with 60 degrees shift. Similarly, here both the secondary windings produce 6 pulses with 60 degrees shift. However, due to the change in configuration of the delta and Y secondary windings, there is a phase difference in their output line voltages. The output of the delta connection leads by 30 degrees. By combining the full-wave rectified secondary voltage pulses of the delta and Y connections, we can obtain 12 pulses with a 30 degrees phase shift. Therefore, the full-wave rectification gives a total of 12 pulses per period. The nominal ripple is 3.4%. However, in practice, ripple less than 10% is achieved. Three-phase generators are more efficient and allow for much higher tube output than single-phase generators. We will next summarize the ripples of the 1, 2, 6 and 12 pulse waveforms. Ripple. Ripple is the measure of variation of kilovoltage from maximum. Usually ripple is expressed as percentage of maximum kV. For single-phase rectified output, it is always 100%. This is because the single-phase rectified output kV ranges from maximum to 0. For 3-phase 6-pulse rectified output, it is 13 to 25%, and for 12-pulse rectified output, it is 3 to 10%. Finally, we will briefly discuss the generator power rating before we finish this tutorial on Introduction to Line Frequency Generators. Generator power rating. The generator power rating is always measured under load. The generator power output is expressed in kilowatt. This output kilowatt changes with kVp. For 3-phase generators, the kilowatt rating is obtained by dividing the product of kV and mA by 1000. In case of single-phase generators, this equation is further factored by 0.7 times to account for its RMS value. Since the kilowatt output changes with kVp, as a standard the kilowatt output is measured at 100 kVp. The generator power rating is defined as follows. For an X-ray generator or an X-ray tube focal spot, the power rating in kilowatts is the average power delivered by the maximum tube current in mA at 100 kVp and 0.1 second exposure time. The maximal tube current for high-powered generators can exceed 1000 mA or 1 ampere for short exposures. Thank you for watching this tutorial video on Introduction to Line Frequency X-ray Generators. I hope you found it helpful in understanding the topic covered here. If you have any questions or feedback, please feel free to leave them in the comments section below. Your suggestions will help me create more informative and useful content in the future. Thanks again for your time and attention.